You're watching QVC, the best infomercial channel for all products calculus.
Have you ever been given a Maclaurin series for G and wanted to find out where it converged? Well, now you can using the brand new ratio test. This amazing new product called the ratio test tells you to take the limit as n approaches infinity of the series with n plus 1 plugged in for n divided by the original series. Now, make sure when you remember to do the ratio test that you keep the series inside an absolute value sign. This will be helpful later when we try to find the actual interval of convergence. How do you use the ratio test, one might ask? Well, I'll tell you. Once you get your answer for the limit for the ratio test, it'll converge if the absolute value of this new series is less than 1. Now let me give you a quick demo of the ratio test in action. So, for this series that we have been given at the beginning, we start by plugging in n plus 1 for every single n in the series. Now, make sure when you plug in an n plus 1 to everything, put it in parentheses so you remember to distribute certain numbers later and so you don't miscount or leave any constants out. After you plug in the n plus 1 to the original series, make sure that you divide this new series by the original series. Now let me give you a quick tip here. Since we have two fractions divided by each other, and this looks pretty complex and it's hard to simplify, what we're going to do is we're going to multiply by the reciprocal to make it better to cancel out any like terms or anything such as. One user tip I will give you for this fabulous new ratio test is to make sure you use absolute values on every single step to make sure you don't forget it later on when you need it to find your endpoints. Our next step is to distribute the 2 into the n plus 1 on the top and the bottom so that we have the right terms. And then what we're going to do is split the exponents that have a plus, as in n plus 1, to make sure that we can better cancel out like terms for the left and the right series. Our next step is to cancel out terms that are like or can be canceled, as in negative 1 to the n and x to the 2n, and with the x cubed over the x, we can cancel out one of the x's on the bottom and leave x squared remaining on the top. We're going to rewrite what we have remaining so that we can better take the limit and understand each piece as n approaches infinity. Now that we have this limit complete, we're going to look at the n's as they approach infinity. Since we have a 2n on the top and a 2n on the bottom, we have equal powers for the top and the bottom, meaning that we take the leading coefficient as the answer to our limit. Now in this case, the leading coefficient is anything that is not an n that is multiplied by the n terms. So since we have a 2 on the top and a 2 on the bottom, those cancel out to leave us with just negative x squared as the only remaining term. Now, since this negative x squared is in the absolute value, and this absolute value has to be less than 1 to find the interval of convergence, what we're going to do is get rid of the negative for the negative x squared, so we're remaining with x squared has to be less than 1. Now, since x squared has to be less than 1, what we're going to do is we're going to split it, so we just find our x. So that means x has to be greater than negative 1 or less than 1 for x squared to be less than 1. Fun fact, if you order the next 10 minutes, you can check your endpoints, which are a crucial part of the ratio test package. So now that we have our negative 1 is less than x, which is less than 1, as our general interval of convergence, we have to see if the endpoints behave the same way. So first we're going to look at this x equals negative 1, and for each x we're going to plug negative 1 into the original series. Now, once we split apart the negative 1 to the 2n plus 1 into negative 1 to the 2n and negative 1 to the power of 1, we notice that the negative 1 to the 2n will always be positive because you will always get an even exponent right there. This negative 1 to the 1 will always be negative, but this negative 1 to the n in the middle here, this will always alternate, meaning that we have to do the alternate series test to see if it converges. Now, the alternate series test says that it has to alternate, which this does, that the terms decrease in magnitude, which this does. If we keep adding up numbers plugging in n, we will get smaller and smaller numbers. And the terms have to approach 0, which obviously if they're getting smaller and smaller, they will eventually approach 0. So since this series with -1 plugged in checks out for all three things, that means that it converges by the alternating series test. Now, if we didn't catch this, the terms decreasing in magnitude and approaching 0 came from it being bottom heavy. Now that we know that the series converges when x equals -1, we can make it -1 is less than or equal to x in the interval of convergence. Now we have to test the other endpoint, x equals 1. So doing the same thing we did before, we're going to take the original series and plug in 1 for the x. Now, quickly you can notice that 1 to the power of anything will be 1. So this region right here will always be 1, meaning that we can kind of ignore it because it will never change. Now this -1 to the end, however, alternates. So once again, we will be performing the alternating series test to see if it converges. Obviously, once again, it alternates, the terms decrease in magnitude, and the terms are approaching 0 due to it being bottom heavy. And as in the other endpoint, it's the same amount of bottom heaviness, which doesn't really matter in this case because it'll be bottom heavy regardless. So now that we know that the x equals 1 endpoint converges by the alternate series test, that means that both of the endpoints are in the interval of convergence, meaning the interval of convergence is finally -1 is less than or equal to x, which is less than or equal to 1. As you can see, this fabulous ratio test is the best product there is now. If you want to find any interval of convergence, this is the way to go. If you want to buy now, call 1-234-567-8900.
When looking into new Calc BC problems, it can be a long process determining which ones are worth the investment based on their error. Using our alternating Maclaurin series for g at x equals 1/2, experts have ensured that the approximation differs from g of 1/2 by less than 1/200th, and therefore is a very reliable solution. In order to prove it, the prompt tells you that the first two terms of the series were used to get 17 over 120, which was solved by plugging in 1/2 for x and a 0 and 1 for our n values. Now, in order to find the error, experts use the alternating series error bound since the series is alternating and decreasing in value. The error bound tells us that the next term in the series would be the max error, so all you have to do is plug in a 2 for n, since the first two terms used were a 0 and 1. If you do this and simplify, you get 1 over 224, which is definitely less than 1 over 200. And there you go. This problem won't only help you with newer topics, it'll also score you 2 points on an FRQ, so purchase today.
Have you ever had to write the first three non-zero terms and the general term of the Maclaurin series for g prime of x, but you were only given g of x? Well, fear not. Introducing our newly developed g prime of x. Using our derivative power rule, our mathematicians developed the perfect general term for you. Here's how our mathematicians developed g prime of x. First, they kept the same series from n equals 0 to infinity. Next, they kept the -1 to the n. Since it doesn't depend on x, we treat it kind of like a constant. We also kept the 2n plus 3 because of the same reason. Now we deal with our x term. We're going to take the exponent and bring it in front because of the derivative power rule. Now we write our x, and we have to subtract 1 from the original exponent. So that just leaves us with 2n. Now that you have your g prime of x, let me show you the ways you can use it. What if you needed to find the first three non-zero terms? You start by plugging in 0 for n because the series says n equals 0 to infinity. And then each time you plug in, you add 1 to n until you have 3 terms. In this case, we will be plugging in 0, then 1, then 2. All that's left to do is simplify, so you'll end up with P3 of x equals 1/3 plus negative 3x squared over 5 plus 5x to the 4th over 7. So make sure to buy your G prime of x today so that you can solve any FRQ that calculus throws at you.